Hello students, welcome to Interconnecting Physics. Today I will teach you about electric field, units of electric field due to point charge, superposition principle for electric fields, continuous distribution of charge and electric field due to a uniformly charged ring. So without wasting time, let's get started. For regular updates, you can follow me on given links. So these are the topics which are to be covered today. So what is electric field? It is the space around a point charge within which its influence can be felt by the other small charge is called electric field. So let us explain by taking examples. Suppose we have two charges. One is Q1 and another is Q2. If these two charges are nearer to each other, then they will feel some kind of force. If both are positive, they will repel each other. If both are negative, they will also repel each other. If one is positive and one is negative, then they will attract each other. So this happens due to electric field because there is, suppose we have a charge and there is always a kind of force present around a charge. When another charge comes near this charge, it feels some kind of force. Maybe force of repulsion or force of attraction, that depends upon the sign of these two charges. And this happens due to electric field. So we say electric field is the region around a charge up to which its effect can be experienced by another charge. Means if another charge comes in this area, comes in this region, then it will feel some kind of force, and that is called as electric field. So that's why the definition is the space around a point charge within which its influence or its effect can be felt by the other small charge is called as electric field. Now what is source charge? The point charge producing electric field. The charge which is producing electric field is called source charge. And the test charge, the infinitely small charge experience an electric force in the electric field of source charge is called test charge. Means the charge which is feeling that some kind of force is called as test charge. So we see here, suppose we have a source charge and we have a test charge at point P. So source charge is creating electric field and exerting force on test charge. If test charge is nearer to this source charge, nearer means if test charge is in the region around this source charge, then only then it will feel some kind of force. And if it is outside the region of the source charge, it will not feel any kind of force. So this was the electric field. Now what is electric field intensity? See, electric field intensity and electric field is one and the same thing. So let us now define its formula. So electric field intensity due to a static charge at a point is the force experienced by test charge. So E vector, it is denoted by E vector and it is a vector quantity which is equal to limit Q naught approaches to 0 F vector divided by Q naught. Why limit approaches to 0? Because Q naught should be very near to 0. Means it is not 0 but it's very near to 0. Means it is very small. It is infinitely small. And why is it small? Because if it is large, if we take Q naught as large, it may exert a large force on the source charge. It may exert a large force on the source charge and hence the position of the source charge will change and it will disturb the position of the source charge. Maybe source charge can move anywhere due to this force of the test charge. So because of this, electric field due to source charge on the test charge will change and will not be able to measure the exact value of the electric field if test charge is taken to be large. That's why we take test charge is to be small so that it exerts a very small force on the source charge and source charge does not change its position, and in turn it's very easy for us to measure the electric field of the source charge. So come to the definition. So electric field is the limit Q naught approaches to 0 F vector divided by Q naught, means it is the force experienced by the test charge in the field of the source charge. So SI units of electric field intensity is Newton divided by Coulomb. Since F is measured in Newton and Q naught is measured in Coulomb, so Newton per Coulomb or Newton Coulomb inverse. And the dimension formula we write as MLT minus 2 for force, and for Q naught it is AT. So MLT minus 3, T minus 3, because in the denominator the T has power 1, and when we take this T in the numerator, the power will be added with this another T, and it will be T minus 3, and similarly for A minus 1. Q naught has dimension formula AT. If you want to know this, then click on the I button and watch the video. Now, electric field is a vector quantity. Now see, next topic is electric field intensity due to a point charge. Now there are two cases. Case 1, when source charge is at origin, and number 2, when source charge is away from the origin. So let us discuss the electric field intensity due to a point charge when source charge is at origin. So for this, let us consider we have a coordinate system O, X, Y, Z, and the source charge is placed at origin O. Now we take the test charge at point P at a position vector R vector from the origin O. Now the force acting on this test charge due to this source charge, because Q naught is in the region of electric field of source charge. So now it will experience some kind of force which is given by Coulomb's law. So we write Coulomb's law as F vector equal to 1 over 4 pi epsilon naught. There are two charges, capital Q, small q. So capital Q, Q naught divided by R square, and the direction is given by a unit vector, that is R cap, and it is along OP. It is along OP. Now the electric field experienced by test charge is given by E vector equal to F vector divided by Q naught. Now put the value of F vector from this equation number 1, and you see here Q naught cancels out with another Q naught, and we are left with 1 over 4 pi epsilon naught Q divided by R square into R cap. Now the magnitude of electric field is given by 1 over 4 pi epsilon naught Q divided by R square, because the unit vector has magnitude equal to 1. So this is the formula for electric field due to a point charge when source charge is present at origin. Now you see from this relation that electric field due to point charge only depends upon source charge. Only depends upon source charge. It does not depend upon test charge. And number 2, electric field intensity is inversely proportional to R square, means if R approaches to infinity, then E will approach to 0. So this means electric field has infinite range. Electric field has infinite range. Now, these are the graphs between electric field and square of the distance, and graph is like this, and never touch this graph with y-axis as well as with x-axis. Now you see graph between E and 1 over R square, it is a straight line passing through the origin. Now case 2, when source charge is away from the origin. You see, for this let us take coordinate system O, X, Y, Z, and we have source charge at point A, we have test charge at point B. Let R1 vector is the position vector of the source charge, R2 vector is the position vector of the test charge. So Coulomb force experienced by test charge in the field of this electric field of source charge. So we write it as F vector equal to 1 over 4 pi epsilon naught Q naught. Now the distance between source charge and test charge is AB. So AB modulus square, and the direction is given by RAB unit vector, because Q is exerting force on Q naught. Q is exerting force on Q naught. So direction will be from A point to B, which is given by RAB unit vector. Now, using equation 2 and 3 in equation number 1 means we have to apply the triangle law of vector addition in triangle OAB. Then we will find the value of R unit vector. So OA plus AB vector equal to opposite vector, that is OB vector. Now keep AB in the left hand side and take OB in the right hand side. Now put the value of OB, which is R2 vector, and put the value of OA, which is R1 vector. Now AB modulus will become R2 minus R1 modulus. Now what is the value of RAB unit vector? You know, according to definition, unit vector is given vector divided by its magnitude. Now put the value of vector, that is R2 minus R1 vector, and the magnitude R2 minus R1 modulus. Now put these values in equation 1. So you will get 1 over 4 pi epsilon naught Q naught divided by AB square, that is R2 minus R1 modulus square, and put the value of R cap, which is R2 minus R1 divided by R2 minus R1. Now these base are same, so power can be added. So we can write 1 over 4 pi epsilon naught Q naught R2 minus R1 vector divided by R2 minus R1 whole cube. Now this was the force. So now the electric field due to source charge Q at point P. Because what is electric field? It is simply, you can write F vector divided by Q naught. So put the value of F here. So we see Q naught, this Q naught will cancel out with this Q naught, and the result will be 1 over 4 pi epsilon naught Q R2 minus R1 vector divided by R2 minus R1 whole cube. So this is the value of electric field in terms of position vector. So we see in this relation, electric field does not depend upon the test charge, it only depends upon the source charge. Now let's see further Cartesian rectangular components of electric field intensity due to a point charge. So for this, let us consider we have a coordinate system O, X, Y, Z. Let Q source charge is present at origin, and there is a point P having coordinates X, Y and Z, and suppose test charge is placed at point P. So the electric field has rectangular components Ex, Ey, Ez. Ex is along x-axis, Ey is along y-axis, and Ez is along z-axis. Now let us say R vector is the position vector of the point P from the origin O. So we know that electric field due to point charge is given by this relation. You know, we did here this formula, you remember, E equal to 1 over 4 pi epsilon naught Q over R square in magnitude form, and E equal to 1 over 4 pi epsilon naught Q over R square R cap in vector form. So we use this formula here. Now you write R cap as R vector divided by its magnitude. And when we write this, we see R square becomes R cube because it gets multiplied with this R. Now substitute the value of E vector and R vector and modulus of R. Now you see E can be written as Ex I cap, Ey j cap and Ez k cap. And R vector we write as X I cap, Y j cap and Z k cap. And the modulus is written as x square plus y square plus z square under root. We write here R equal to x square plus y square plus z square under root. So substitute all these values in this equation number 3. So we will get 1 over 4 pi epsilon naught Q x I cap plus y j cap plus z k cap divided by x square plus y square plus z square raised to power 3 by 2. Now compare the coefficients of I, j and k on both sides. But before doing that, we separate these x, y and z. Means we separate the coefficients of I cap, j cap and k cap. So after that, when we compare the coefficients of I, j and k, we will get Ex equal to 1 over 4 pi epsilon naught Qx divided by x square plus y square plus z square raised to power 3 by 2, and in the similar manner Ey and Ez can be calculated. Now note that for x equal to y equal to z, if we put x equal to 2, y equal to 2, z equal to 2. So you see the value of Ex, Ey and Ez, all values will become equal because there is only one difference in this equation, that is x, y and z. All the rest of the terms are same. So it means for x equal to y equal to z, the Ex equal to Ey equal to Ez. And this relation tells us that electric field intensity due to a point charge is spherically symmetric. Means if we make the coordinates same, then we see that the value of electric field is same at every axis, and this means electric field intensity due to point charge is spherically symmetric. So now come to the next topic, that is electric field intensity due to a system of charges, which is called principle of superposition. If you want to know about principle of superposition of Coulomb's law, then hit the I button and watch that video. Now, according to the principle of superposition, net electric field at a point charge due to a group of point charges is equal to the vector sum of the electric field intensities produced due to individual charges at that point. So for this, we have a coordinate system O, X, Y, Z, and we have a number of charges Q1, Q2 up to so on Qn. You know, n can be 100, n can be 1000. But for our convenience, we take only 3 charges, that is Q1, Q2 and Q1, because it's very difficult to show all of the charges in this single page. So we take only 3 charges, that is Q1, Q2, Qn. Let R1 vector is the position vector of Q1, R2 vector is the position vector of Q2 and Rn is the position vector of Qn from the origin O. Let us say we have a test charge Q0 at point P whose position vector is R0 vector from the origin O, and at point P the test charge. So we have to calculate the electric field, the total electric field on this test charge due to all the charges. Suppose Q1 is exerting electric field, exerting force on Q0, and Q0 is experiencing force in the field of Q1, so we write it as E1. If Q0 is feeling some kind of force due to Q2, so we write it as E2. And similarly, if Qn is exerting some kind of force on Q0 and Q0 is experiencing some force in the field of Qn, then we write it as En. So, you know, the electric field due to a point charge in terms of position vector is written as like this. We did in this topic when source charge is away from the origin. So we use this relation in this superposition principle. So E1, it is the electric field intensity at charge Q0 due to Q1, which is 1 over 4 pi epsilon naught Q1, because we saw in electric field due to point charge that electric field does not depend upon the test charge. It only depends upon the source charge. So here source charge comes. So E1 is R0 minus R1 vector divided by R0 minus R1 whole cube. Similarly, E2, which is 1 over 4 pi epsilon naught Q2. Now source charge is Q2. R0 minus R2 vector divided by R0 minus R2 Q. Similarly, electric field intensity due to charge Qn at charge Q0 is En vector equal to 1 over 4 pi epsilon naught Qn, because this time Qn is the source charge, and R0 minus Rn vector divided by R0 minus Rn whole cube. Now net electric field at point P, we add all the values. That is E vector equal to E1 vector plus E2 vector plus up to so on En vector. Now substitute the values from equation 1, 2 and n in this equation. We get 1 over 4 pi epsilon naught q1 r0 minus r1 over r0 minus r1 whole cube plus 1 over 4 pi epsilon naught q2 r0 minus r2 vector divided by r0 minus r2 whole cube plus up to so on plus 1 over 4 pi epsilon naught qn r0 minus rn vector divided by r0 minus rn whole cube. So this is the final relationship which shows the net electric field on the test charge due to all other charges around it. So if you want to write this relation in the summation form, then we can write in this manner. We take 1 over 4 pi epsilon naught out of the summation because 1 over 4 pi epsilon naught is common in every term. So it can be taken out from the summation. And the limit I starts from 1 to n. We write q1, q2, qn as qi. R0 is same in every term, so it is written as such. Minus r1, r2, rn is written as ri divided by r0 minus ri whole cube. So this is the superposition principle in terms of summation. So let's come to the next topic. It's a very important topic, that is continuous charge distribution. Students, please note that continuous charge distribution comes under macroscopic system. Macroscopic system. What is macroscopic system? Anything which can be seen by naked eye, which can be seen normally. If you see table, if you see chair, you see copy, you see your mobile, you see your laptop with your naked eyes. So this is the macroscopic system. So continuous charge distribution means a system of closely spaced electric charges is called as continuous charge distribution. Means system of closely spaced electric charges. Means electric charges are so close to each other that is, it is very difficult to differentiate one charge from another, and the space is negligibly small. There is no space in the charges, and we see this system seems to be like continuous. So this is called continuous charge distribution. It means a system in which charge is uniformly distributed. Uniformly distributed means space is not seen in the charge. It is very difficult to differentiate one charge from another. All charges look like same. So it is uniformly distributed over the conductor. In such type of distribution, infinite number of charges are closely spaced. Infinite number. So it means at macroscopic level, charges are so large in number that practically in this macroscopic system means at this stage it's not possible to count a number of charges. So quantization here ignored. So in quantization we saw Q equal to NE. E is the basic charge, which is 1.6 into 10 raised to power minus 19 Coulomb, and N is the integer, which can be negative integer, positive. Suppose N is 100. So we multiply 100 into E and we get the charge. But in macroscopic system, charges are so large in number, that we cannot calculate the number of charges. We don't know how many charges are present over here. So quantization principle is ignored in macroscopic level. Quantization system is only acceptable in microscopic system. Microscopic. When we talk about electrons, protons and subatomic particles, very small sizes like 10 raised to power minus 15 meter, 10 raised to power minus 10 meter. So such system come under the category of microscopic systems. Okay. So now come to the topic. Continuous charge distribution can be on a line, can be on a surface, can be on entire volume. If the charge varies linearly, means charge varies one-dimensionally along the length of the conductor, it is called linear charge density. And if the charge is uniformly distributed on the surface of the conductor, that is two-dimensional, 2D, then it is called as surface charge density. And if the charge changes with the volume of the conductor, then it is called as volume charge density. So linear charge density is defined as charge per unit length. It is denoted by lambda. Lambda equal to charge divided by length, and the unit SI unit is Coulomb divided by meter, Coulomb meter inverse. Similarly, surface charge density is charge divided by area. In linear charge density divided by length, in surface charge density divided by area, it is denoted by sigma, and sigma is Q divided by A, and the SI unit of sigma is Coulomb per meter square, that is Coulomb meter inverse square. And the volume charge density, it is defined as the charge per unit volume. It is denoted by rho, and the rho is Q divided by volume, and the SI unit is Coulomb per meter cube, that is Coulomb meter inverse cube. Now, electric field intensity due to continuous distribution of charge. So, number 1, electric field intensity due to linear distribution of charge. Okay. So, let us consider we have a wire of length AB over which the uniformly charge is distributed. Now let us consider a small length element. So why we consider small length element? Since it is continuously charged distribution. It is the example of continuously charged distribution, or continuously charged distribution charges are large in number. Okay. And we can't count the charges. So if we can't count the charges, then how can we measure the electric field at point P due to this whole wire? So in order to solve this problem, we have to consider a small length element having length dl, and charge present over here is dq. So lambda will be here, dq charge divided by length, that is dl. So the charge will be, if you cross multiply this relation, lambda into dl. Let point P having test charge Q0 is present at a distance r vector from this length element dl. So dq will be lambda dl. Now the electrostatic force on the test charge Q0 due to this small length element is denoted by df vector, small force, equal to 1 over 4 pi epsilon naught dq into q0, because here charge is dq and here charge is q0. So dq into q0 divided by r square into r cap, which is given by Coulomb's law. Now the electrostatic force on q0 due to the whole wire, so we use integration. So f vector equal to integration of df. Now substitute the value of df and substitute the value of dq, which is lambda dl, from equation number 1. Now take constant terms outside the integration. Q0 is constant, 1 over 4 pi epsilon naught constant, so they can be taken out from the integration, and we are left with integration of lambda dl divided by r square into r cap. Now the electric field intensity, because we have to calculate the electric field intensity. If you want to calculate the force, then this derivation will end at this point. But if you want to calculate the electric field intensity, then further with one line we will end up with this derivation. So electric field intensity due to a linear charge distribution at distance r is, you know the formula for electric field, that is F vector divided by Q0. Substitute the value of F vector. This Q0 will cancel out with this Q0, and we will be left with E vector equal to 1 over 4 pi epsilon naught integration of lambda dl over r square into r cap. So this is the electric field intensity at a point P due to continuous distribution of charge, that is linear distribution of charge. This lambda shows linear distribution of charge. Okay. Now number 2, the electric field intensity due to surface distribution of charge. For this, let us consider a two-dimensional surface, and let us consider a point P at which charge Q0, test charge Q0 is present. Now the charge has been continuously distributed over this surface. Since continuously distributed, so we cannot count the charge. To solve this problem, we have to take a small area element, that is ds, okay, at a distance r vector from point P. Now because sigma is charge divided by area, so charge will be on this point is sigma into ds. So here charge is dq. Now The electrostatic force on test charge Q naught at point P due to this small area element is dF vector equal to 1 over 4 pi epsilon naught dq into Q naught divided by r square into r cap given by Coulomb's law. Now the total electrostatic force is given by integration of dF. Substitute the value of dF and put the value of dq, that is sigma into ds. Now take the constant term outside the integration. Now let us calculate electric field intensity due to surface charge distribution at a distance r is given by f vector divided by q naught. Substitute the value of f vector, take the constant terms outside, and we will get 1 over 4 pi epsilon naught in integration of sigma ds divided by r square into r cap. This q naught cancels out with this q naught. Now you see this sigma shows the surface charge distribution. Now let's have third point, that is electric field intensity due to volume charge distribution. For this we take a three-dimensional body and over which a uniformly charge has been distributed, maybe positive, maybe negative, and at point P charge Q naught is present over at a distance r vector from the small volume element which we have considered here. Now rho is given by volume charge distribution is charge divided by volume. So the charge on this element will be rho into dV, rho into dV. So now let us calculate the small force due to this volume element on this test charge, which is given by dF vector equal to 1 over 4 pi epsilon naught dq into q naught divided by r square into r cap, and the electrostatic force on q naught due to whole volume is given as f vector integration of dF vector equal to 1 over 4 pi epsilon naught. Put the value of dF here and substitute the value of dq here and take the constant terms out from the integration. Now electric field intensity due to volume charge distribution at a distance r is given by f vector over q naught. Substitute the value of f vector and q naught cancels out with this q naught. Take the constant term outside and we will be left with E vector equal to 1 over 4 pi epsilon naught rho dV over r square into r cap. This rho shows the volume charge distribution. You see, the method of calculating is same in linear charge distribution, is same in surface charge distribution, is same in volume charge distribution. The only difference is this. Only difference is lambda dl and the diagram. Only difference is sigma ds and the diagram. And the only difference is rho dv and the diagram. All the procedure is same in these three steps. Now let's get on the another example of the continuous charge distribution, that is uniformly charged ring or circular loop. This is also the example of continuous charge distribution. So topic is electric field intensity due to a uniformly charged ring or circular loop. It means we are given with some circular loop and we have to calculate the electric field of this loop at point P. So let us consider a uniformly charged ring having radius A and the lambda is the linear charge density here, and let P is the point on the axis of the ring at a distance x from the center of the ring. Axis means which is passing through the center and is along x-axis. Now let us consider a small element of length dl. The procedure is same. We have to take length element. If it is linear charge distribution, then we have to take the length element. So let us say we have a length element of length dl, then the charge present over here will be dq equal to lambda into dl. Now the electric field intensity at point P due to this small length element is given by 1 over 4 pi epsilon naught dq over r square. Put the value of dq, which is lambda dl over r square. Now the value of r square can be calculated from this right angle triangle using Pythagoras theorem. So let us say point P is at a distance r from this length element, then r square equal to, using Pythagoras theorem, hypotenuse square equal to base square plus perpendicular square. So substitute the value here. You get dE equal to 1 over 4 pi epsilon naught lambda dl over x square plus a square. Now the direction of DE, you see direction of DE is along AP, radially outward. Now DE makes an angle theta with the axis of the ring. This DE is making an angle theta with the axis of the ring. So resolve DE into two components, and you know horizontal component is represented by cos theta and the vertical component is represented by sin theta. Now you see this DE cos theta component is the horizontal component and this is vertical component. Now if we take this DL here, then there is equal and opposite element will be present here, DL. And due to this length element, the direction of the electric field will be given by this. And when we resolve this DE into two components, you see DE sin theta is vertical component and DE cos theta is the horizontal component. So we see here the DE cos theta components are added up, but the DE sin theta components both are equal and opposite, so they cancel out each other. If this ring is made up of such elements, then if DL is present over here, then DL will also be present here. If DL is here, then DL is also present here, 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 here. So you see every time the DE cos theta component will be added up, but the DE sin theta component every time will be equal and opposite and will cancel out each other. So this ring is made up of many such charged elements. Every time the horizontal component of the electric field DE due to all other charged elements will be added up because they are in the same direction. But DE sin theta component of DE will be cancelled by other DE sin theta component as they are equal and opposite in direction. You see, therefore, the net electric field at point P due to the whole ring is given by E equal to integration of whole ring dE cos theta, because dE has been resolved into two components, dE cos theta and dE sin theta. Now dE sin theta, because of equal and opposites, cancels each other, but this dE cos theta every time is added up with another dE cos theta. So we see here it is the integration of dE cos theta. Now substitute the value of dE from equation number 1, which is 1 over 4 pi epsilon naught lambda dl over x square plus a square. So when we substitute this value here, we see the equation looks like this. Now put the value of cos theta, which is base over hypotenuse, which is from this triangle you see cos theta, base over hypotenuse. So x over r, and the value of r from Pythagoras theorem is x square plus x square plus a square under root. Now using this equation in equation number 1, we get now using this equation, we see E equal to 1 over 4 pi epsilon naught lambda dl over x square plus a square into, put the value of cos theta, and the value is 1 over 4 pi epsilon naught lambda x over x square plus a square raised to power 3 by 2 integration of dl, because these all are constant terms and can be taken outside the integration. But length dl is not constant terms, because we are we are solving problem on length of the circular loop. Now length of the circular loop or length of the circle is circumference of the ring, which is given by 2 pi into radius, and here the radius is denoted by small a. Now put this value in this equation, you get 1 over 4 pi epsilon naught lambda x divided by x square plus a square into 3 by 2 raised to power 3 by 2 into 2 pi a. Combine lambda and 2 pi together and see what is lambda. It is the charge divided by length. If we are talking about whole ring, okay, and lambda is charge divided by length, that is length of the loop is 2 pi a. and the lambda into 2 pi a will be equal to charge on the ring. So lambda into 2 pi a will be charge on the ring, which is denoted by Q, total charge, because here we are calculating total electric field. So now this becomes Q. So the relation is E equal to Qx divided by 4 pi epsilon naught brackets x square plus a square raised to power 3 by 2. So direction of electric field intensity at a point due to charge is along the axis of the ring. Means this side, because d cos theta is added up and the direction is along OP, that is positive axis of the ring. Now special case is if x is very greater than a. So you see from the diagram, if x is very greater than a, means radius of the loop is very small and the observation point is very far away from the center of the loop. So we can neglect a, we can neglect radius. So you see from this relation, if we neglect, the relation is 1 over qx over 4 pi epsilon naught x square plus a square raised to power 3 by 2. If we neglect a, we will be left with qx divided by 4 pi epsilon naught x square raised to power 3 by 2. 2 cancels out with 2 and we left with qx divided by 4 pi epsilon naught x cube. One x cancels out with another x and the relation is 1 over 4 pi epsilon naught q over x square. You see, we know from electric field due to point charge, the electric field is 1 over 4 pi epsilon naught source charge divided by r square, and this relation is same as that of this relation. So we can conclude, if the observation point is very far away from the center of the loop, then this ring will behave as point charge. This ring will behave as point charge and the relation looks like E equal to 1 over 4 pi epsilon naught q over x square. So this is the same as that of electric field due to a point charge. Number 2, if the point P lies at the center of the ring, means this point P comes here. So x will be 0. So if we substitute the value x equal to 0, the whole of the equation will become 0. So means electric field at the center of the circular loop is 0. Now the maximum value of electric field intensity, it will be maximum only when if differentiation of electric field with respect to x equal to 0. Now put the value of E here and do the derivation. We see x equal to plus minus a divided by under root 2. Now this calculation is not so important, but this point is very important, that at x equal to plus minus a by under root 2. So let's see in the graph, if x is plus a by under root 2 or x is minus a by under root 2, we see the electric field is maximum here. So means electric field intensity due to uniformly charged ring will be maximum at x equal to plus minus a by under 2 from the center of the ring on the either side of its axis. Means this side or this side, the value will be maximum on both sides. So this was all about today's video. Thank you very much. If you want PDF notes, you can tell me in the comment section or you can follow me on Telegram. Don't forget to like, share and subscribe. Stay happy, stay healthy.